The creatures responsible for every gallon in your gas tank lived in a world completely alien to anything dinosaurs ever experienced. While you've been imagining massive reptiles melting into petroleum, the real creators were organisms so tiny they exist in a realm invisible to the naked eye. These microscopic marine creatures lived in numbers that make dinosaur populations look insignificant, and their deaths created biological events that dwarf any extinction in Earth's history. Picture ancient oceans stretching across vast continents, their surfaces shimmering under primordial sunlight. The most important life forms weren't large creatures swimming through these waters, but microscopic plants called phytoplankton, single-celled algae no bigger than the period at the end of the sentence, and tiny animals called zooplankton that drifted through the water column like living dust. These organisms existed in concentrations so dense that the water itself took on different colors when viewed from above. Diatoms, a particular type of algae with intricate glass-like shells, populated these ancient seas in numbers that challenge human comprehension. A single drop of seawater could contain thousands of these organisms, and they reproduced at rates that allowed their populations to explode across entire ocean basins within weeks. Unlike dinosaurs, which required years to reach maturity and produced relatively few offspring, these microscopic creatures could double their populations daily under optimal conditions. The abundance comparison between these marine microorganisms and dinosaurs reveals the absurdity of the petroleum myth. Researchers estimate that plankton biomass dwarfs dinosaur biomass by enormous margins, which explains why oil volumes demand far more microorganisms than land animals could ever provide. Paleontologists calculate that all dinosaur species combined over their entire 165 million year reign produced perhaps a few billion tons of total biomass. Meanwhile, the phytoplankton and zooplankton in just a single ancient ocean could generate more biomass in a single year than all dinosaurs produced in a millennium. When these tiny creatures died, they didn't perish individually like large animals. When algae blooms collapsed, trillions of cells sank and built vast organic layers underwater. Seasonal changes, volcanic eruptions, climate shifts, or simple nutrient depletion could trigger die-offs involving trillions of organisms simultaneously. These death events occurred on scales that make the asteroid impact that killed the dinosaurs seem modest by comparison. The mystery of how something so impossibly small could create something so valuable lies in the unique properties of marine microorganisms. Unlike dinosaurs, which were composed largely of bones, muscles, and other structures that decompose rapidly, these microscopic creatures contained high concentrations of lipids, proteins, and hydrocarbons that could survive the initial stages of decay. Their cellular structures were already rich in the carbon and hydrogen compounds that would eventually become petroleum. The conditions required for oil formation strongly favored these marine organisms over any land-dwelling dinosaurs. Oil creation demands environments with limited oxygen, rapid burial, and specific chemical conditions that existed almost exclusively in ancient ocean basins. Terrestrial dinosaurs lived and died in environments where oxygen-rich conditions promoted complete decomposition, breaking down organic matter into carbon dioxide and water rather than preserving it for petroleum formation. The timing of major oil deposits further proves the marine origin of petroleum. The most productive oil-forming periods in Earth's history occurred when vast shallow seas covered much of the planet's surface, creating ideal conditions for marine microorganism blooms and subsequent die-offs. These periods, including the Carboniferous and Permian eras, featured global ocean conditions that supported massive populations of algae and plankton while providing the anoxic seafloor environments necessary for organic matter preservation. Ancient bacteria played crucial roles in these underwater ecosystems, both as oil precursors themselves and as processors of other organic matter. When bacterial populations crashed along with algae and plankton, their cellular remains contributed additional hydrocarbons to the accumulating organic deposits. These bacterial contributions were particularly important because bacteria concentrate lipids and other petroleum precursors in their cell membranes and storage structures. The geographical distribution of oil deposits confirms this marine origin story. Major petroleum reserves consistently occur in areas that were once covered by ancient seas, particularly in regions where oceanic conditions favored high biological productivity. The sedimentary rocks that contain oil formed from accumulated marine sediments and their geological signatures clearly indicate underwater deposition environments incompatible with dinosaur habitats. Modern oil exploration techniques can identify the specific types of organic matter that form different petroleum deposits, and these analyses consistently point to marine microorganisms as the primary source. Geochemical fingerprinting of crude oil reveals molecular structures that could only have originated from algae, plankton, and bacteria, rather than from complex multicellular organisms like dinosaurs. The transformation process that converted these microscopic organisms into petroleum required precise environmental conditions that occurred naturally in ancient marine settings. The organic-rich mud created by dead microorganisms needed rapid burial by additional sediments to prevent complete decomposition. This burial process happened routinely in ancient ocean basins where sediment from rivers and atmospheric dust continuously accumulated over biological deposits. The incredible efficiency of marine microorganisms in creating petroleum becomes apparent when you consider that organisms measuring just micrometers in size generated enough organic matter to power industrial civilization for over a century. Every time you fill your gas tank, you're essentially harvesting the accumulated remains of countless microscopic creatures that lived and died in ancient seas millions of years before the first dinosaur ever walked the earth. Understanding that every drop of oil originated from creatures so small you'd need a microscope to see them completely reframes our relationship with petroleum and reveals just how disconnected the dinosaur myth really is from scientific reality. But knowing what died to create oil is only half the story. The real mystery begins with what happened to these microscopic corpses after they started their long journey toward the ocean floor. The underwater burial grounds. Picture ancient ocean waters turning dark as billions upon billions of microscopic corpses begin their final descent toward the seafloor. These weren't isolated deaths scattered across time, but massive mortality events that transformed entire ocean basins into underwater cemeteries. When algae blooms crashed or zooplankton populations collapsed, the dying organisms created biological snowstorms that could last for months. With microscopic bodies falling through hundreds of meters of water column before settling into thick organic-rich layers on the bottom. The race against decomposition began the moment these organisms died. Bacterial decay worked furiously to break down the fallen microorganisms, and under normal circumstances, this process would completely destroy all organic matter within weeks or months. Aerobic bacteria, which require oxygen to survive, attack dead organisms aggressively and reduce them to basic compounds like carbon dioxide and water. But the sheer volume of dying organisms during these ancient mass mortality events created a critical problem for the bacteria. They consumed oxygen faster than the ocean could replenish it. As oxygen levels dropped in the water column, and especially near the seafloor, aerobic bacteria began suffocating and dying themselves. This created a narrow window of opportunity where organic matter could accumulate faster than bacteria could destroy it. The key factor determining whether organic matter would survive long enough to become oil was the speed of burial beneath subsequent sediment layers. These sediments needed to be buried in oxygen-free basins, like ancient inland seas, so bacteria couldn't fully decompose the organic matter. Ancient ocean basins provided ideal conditions for rapid burial because they functioned as massive sediment traps. Rivers carried enormous quantities of sand, silt, and clay into these marine environments, while atmospheric dust and volcanic ash added additional layers from above. The organic matter from dead microorganisms became sandwiched between these inorganic sediment layers, creating alternating bands of biological and mineral deposits. This layering process was essential because it isolated the organic matter from oxygen-rich water above and prevented bacterial decomposition from completing its destructive work. The formation of source rocks required very specific geological conditions that existed only in certain ancient environments. These rocks formed when organic-rich sediments accumulated in depressions on the ocean floor, where water circulation was limited and oxygen levels remained consistently low. Basins with restricted water flow, such as inland seas or deep ocean trenches, created perfect conditions for preserving organic matter because fresh oxygenated water couldn't easily reach the bottom to fuel bacterial activity. Shallow continental shelves during the Carboniferous and Permian periods, spanning from approximately 360 to 252 million years ago, provided some of the most productive environments for source rock formation. These periods, which occurred long before dinosaurs first appeared, created the vast majority of the world's oil deposits. The areas featured warm temperatures that supported massive populations of marine microorganisms, while their limited depth and restricted circulation created the anoxic bottom conditions necessary for organic preservation. The combination of high biological productivity in surface waters and oxygen-poor conditions on the seafloor made these environments incredibly efficient at converting living organisms into petroleum precursors. The thickness of sediment accumulation played a crucial role in determining whether organic matter would eventually transform into oil. Thin layers of organic-rich sediment often remain too close to the surface, where oxygen infiltration and bacterial activity could still destroy the preserved organic matter over geological time. Successful oil formation required sediment layers that eventually reached depths of several hundred meters to over a kilometer, creating the pressure and temperature conditions necessary for petroleum generation. The burial process occurred gradually over millions of years, with each new layer of sediment adding weight and pressure to the organic matter below. As burial depth increased, the temperature also rose due to the Earth's natural geothermal gradient, which increases temperature by approximately 25 degrees Celsius for every kilometer of depth. This combination of mounting pressure and rising temperature would eventually trigger the chemical reactions that convert organic matter into petroleum, but only if the initial preservation in anoxic conditions had been successful.